Today we are going to be talking about introduction to the recurrent neural network and the applications of RNNs for several business use cases. Now I want to begin that we have focused on many different architectures like deep neural networks and convolutional neural networks, and similar to them, the recurrent neural networks are also a very specific type of neural networks that allows us to do very cool things. So let's get into what are the things it does and how it is different than other neural network models, and what is the specific niche of RNNs and what class of problems that they can solve. So in order to motivate the uses of recurrent neural networks, let's begin with what is typically available to us, which is traditional neural networks, where you have input layer and you have some hidden layers, and then you have an output layer, and that could be an architecture in a deep neural network. So what you typically have, you have an X, and then there is set of weights and architecture that processes, and then you output something, right? Now in this architecture, each input pair and output pair are independent of each other. So for example, the training data that we were using, right, in the images or in the regression problem or in the classification problem, each pair of this training sample are independent. So you pass the first one, you pass the second one, and they are not dependent, and the prediction of this network is not dependent on the sequence or in which way you process that data. So if you have a data set, and you can take that data set and you can process that, but it is sequence independent. Okay. Now there are many class of problems where we need some notion of sequence dependency, and again, if the decision or if the aspect of the problem which requires us to consider the sequence dependency, then this kind of model will be able to handle that, and we will discuss that, but it might not be the best model to model it. And that's where the value of the recurrent neural networks comes into picture, which are basically geared towards solving problems in which the sequence dependency is very, very important. Okay, so again, let's first of all consider some of the applications why the sequence dependency might be important to motivate it. Okay, so one of the problems that I'm showing, which is basically where the RNNs are typically used, is that your input might be a single image. So for example, the image that you see with this dog here, that might be your input. So your input is a single image, and what you need to do as an output is you need to basically have to describe a caption. Okay, and this is the caption that we have that helps describing this image. Now this has been automatically generated by a recurrent neural network. So this is basically from learning from the data, and this caption has been automatically described by a recurrent neural network. So which is a cute little dog sitting in a heart drawn on a sandy beach. That is, I think, is a fairly accurate description of what the image is. Okay, but what I want you to notice is the input is a single image, and the output is a sequence of word. For example, a cute little dog sitting. So this is essentially a sequence of word that has been outputted by this neural network. So even though the input is this, the output is going to be a different word. Now if you give this neural network, which is focused on image captioning, and let's say if you have a very good trained neural network, or specifically a RNN neural network, and if you provide it a different image, right, it will give you a different caption, and that caption might not be of the fixed length. It might be a 4-word or it might be a 20-word caption, depending upon what is there in the image, right? So this is the challenge that you need to solve, that your input could be something like this, but your output could be a sequence of word which is not of fixed length. It could be variable length, and that has to very, in a good way, summarize the overall thing that is happening inside the image. So this is one of the problems where RNNs are used, where the sequence of word, in this case, as in the output, is important. Second example that I want to quickly mention about is where it is widely used popularly online is in sentiment analysis, right? For example, if you go to Amazon, if you go to other online shopping malls, people will basically put their comments, right? Taking those comments, which might be a very, very detailed comment, which might be multiple different sentences. So it's a large sequence of word, and each review might be of different length, and each sentence in each review might be of the different length. But what you need to do is you need to use that information and process this into a single, maybe this information, whether the review was negative review, whether the review was a neutral review, or whether the review was a positive review. Now this class of problems again is known as sentiment analysis, but here it is exactly sort of opposite to what you have. Here the input is a sequence of sentences, a sequence of words, and the output is mainly basically three numbers, right? 1, 2, 3, denoting negative, neutral, and positive. But the thing that I want to emphasize is what we are inputting. We are inputting to this neural network a sequence of words, which is essentially what has been written by the customer online on a website like Amazon. Okay. Here is another example where we might be interested in predicting the prices of stock, okay, which is a time series. And one way to understand, right, or distinguish RNNs from the classical deep neural network techniques, that these are class of techniques which are very, very well suited for time series modeling or dynamic modeling, in which things are changing and sequentially with reference to a given time instance. And if you have that kind of problems where the time, what has happened before impacts what is going to happen in the future, then RNN is a better suited model for that, right? So stock prediction, price prediction, and we will go through some business use cases later on, are one class of problems for the Rnn applications are well justified, and RNN is probably the best architecture to do that. The second, the final example that I want to motivate is basically this example of machine translation, which is right now in a lot of web apps that are there. So what you do here in this is you might be providing input to the algorithm in a form of a different language, and that different language could be Chinese or Hindi. But what you want to get an output of the algorithm automatically is its translated version in English or in Spanish, right? So when we are taking input in one language, and that's a sound bite that we have probably, and then taking that and processing using a neural network and converting that into a completely another language, which is outputted in probably words in your cell phone or in your laptop, then you're doing what is known as machine translation, and that is also an Rnn application or a very good use case for Rnn application, because the input in different languages could be of different length and the output has to be of different length, and it has to make sense. For example, the output English has to make sense with respect to what has been inputted, and when it has to make sense, the sequence of word has to be grammatically correct, or they need to be in a sequence so that the conversion is meaningful and is right? So these are some of the examples of Rnn applications where you can have inputs in the form of sequences, and the output can also be possibly in the form of sequences. So taking all of this, what we have here, what we can describe in general, the basic component of the Rnn architecture is typically an Rnn architecture will take a sequence of inputs, and then it will give you a sequence of output. Okay, and what it begins with, it starts with a sequence marker, okay, and then it ends with a sequence marker. Okay, and then in between, when you have the sequence marker beginning and sequence marker ending, your information is passed from one subunit to another subunit. So there is a passage of information from previous subunits in this architecture that helps us in basically making making semantically good predictions in many of the use cases that we have. Okay, so there are different variations in the overall neural networks that we have, and those different variations could be classified into main disk classes. So one variation is where we talked about image captioning. We have only one image as an input, and we have a sequence of word that is an output. The other one, sequence classification, is many to one, where probably we have basically supplied a sequence of word. For example, in semantic sentiment analysis, a sequence of word was an input, and the output was whether it's a single thing, in the sense like whether it is a neutral, is positive or negative or not. Okay. So again, there are other class of neural network or RNNs that could be used here, which is basically you have many-to-many mappings. So the number of input is many and the number of outputs are many. So you are basically doing the machine translation where the inputs of words in Chinese or Hindi might be different length and the output in English or Spanish might be of different length. Or one of the problems that I will motivate to, for the representation problem, which is the name entity problem, you will have also multiple input and multiple output. So these are the four main possible variations that you can have in Rnn architectures, where the input to output mapping are slightly different. It will be one to many, many to one, or many to many mappings that you can have.